All right, so in our previous video, we looked at a toy electric car moving at a constant rate on a flat surface. And we used that to explore some of these very important physics definitions that we're going to be using throughout the year. We learned about position, which is where an object is at every instant in time. So we looked at every second where that buggy was. And we also looked at displacement, which was the change in position from one time to another. So looking at, okay, where is it at 3 seconds? Where was it at 1 second? What was the change, the delta x there? And then we also looked at this idea of velocity. So once we had this position and time, and we were able to graph that relationship, we could then look at the slope of that position versus time graph to find the velocity, the rate of change of position over time. Both of these are called vector quantities. What that means is they have a size, another word for that is magnitude, and they have a direction. So if I look at, say here I've redrawn our buggy on a flat surface, I picked an origin point. I said right where the buggy's front is my 0 point. I could have picked anywhere, but that seemed like a good place to pick. And I said going to the right in this situation I would call the positive direction, so anything over here would have a positive position. If the buggy somehow started going in reverse, it would then end up with some sort of negative position. And then velocity can also be positive or negative. The buggy was changing its position towards the positive direction, it would have a positive velocity. If, let's say, it was going left, it would have a negative velocity because its position is changing to be more negative. So even if it has a positive position, it could have a negative velocity as that position becomes more negative. And this was all moving at a constant rate. So that was the most basic motion we could think of, something moving in one dimension at a constant rate. Now, most things in real life don't move at constant rates. So now we want to create a model that can help us describe the motion of things that are changing how they move. They're not going the same change in position every second. So let's think of a situation that we could easily measure and figure out that relationship. And one situation is to think of a cart going down a frictionless incline. So basically I'm taking my old situation, I'm replacing my electric buggy with just a cart that's just going to roll without friction down this surface. I'm actually going to move this over here so we have room for our grass. And I'm going to think about, okay, what's going to happen with this object? If I just let this cart go, if I say, okay, time is 0, so 0 seconds, I'm going to say it's not moving. I'm just going to let it go from rest. And I'm going to wonder, so at 0 seconds, it's not moving. What's going to happen to this object? Well, from life experience, I could say, well, it's going to start going down the ramp, but it's not going to go at a constant rate. It starts not moving. It's going to be going slowly, and then it's going to speed up, going faster and faster. As it goes down this ramp, its velocity is going to change. It's going to gain a more positive velocity. And if I were to motion capture that somehow, maybe take a video and look at every second where this cart is, I could make a motion diagram. And I'd find, maybe in this instance, at 1 second, it's here at 2 meters. At 2 seconds, it's all made it all the way to 8 meters. And then 3 seconds, all the way down here at 18 meters. And I'll note some very obvious differences compared to the buggy model. Here, I've gone a greater position in each interval of time. So each of these were 1 second apart, but the buggy has traveled further in space. It's had a greater displacement. 0 to 1 seconds, its displacement was 2 meters. 1 to 2 seconds, its displacement went from 2 to 8. That's a displacement of 6 meters. 2 to 3 seconds, displacement 8 to 18. That's a displacement of 10 meters. So it is no longer traveling at a constant rate. So let's try to apply, though, still some of our key ideas here. that we came up with and see what we get. So we'll start again by, let's try graphing the position versus time of this buggy, or not this cart on this ramp. And while this is not going to end up going in the negative, I'm always going to include the negative on my graph just to remind myself I should always think about direction when dealing with these vector quantities such as position and velocity. So we got time in seconds, position in meters. I want to make sure I can get up to 18 meters there. So we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. Great. And 1, 2, 3 seconds. And this is my 0 position. 1, 2, 3. And 4, 8, 12, 16, 18. And we'll just carry over from our motion diagram. At 0 seconds I was at 0. 1 second I was at 2. 2 seconds I was at 8. And 3 seconds I was at 18. And I'm not going to get these perfect, but pretty close. We're not using graph paper, so it is what it is. And I'll notice immediately that this is not a linear relationship. If I were to try to draw a line here, it would not go through these points adequately. Turns out, maybe use your graphing software, maybe you just figure it out. This is a quadratic. And I could try 80 times and I'm not going to be able to line this up exactly, but this is a quadratic relationship between position and time. So we actually get, it's some sort of t squared relationship here. And if we do the math, we would find that this is 2t squared, because at 1 second, I'm at 2. So put in a 1 there. I need a 2 for my number in front of that. All right, so this is new. The position is no longer linear with time. Twice as much time no longer means twice as much position. We can see that, right? At 1 second, I go 2. 2 seconds is not 4, though. It's not twice as much. It's more than that. 2 seconds is all the way up at 8, 4 times as far. So this is a quadratic relationship between position and time. You can think about, I'm getting faster and faster each second. I'm going to go a further distance, should make sense. So what do we do about the velocity? Previously, we were able to say velocity was delta x over delta t. We cannot do that anymore. That was in that nice case where we had a line, and we can find the slope of a line by doing rise over run. We no longer, sorry about that, we no longer have a line, so we can no longer do rise over run to find the slope, to find the velocity. Instead, we're going to look at something called the tangent line. And that is a mathematical idea of thinking about, if you imagine at one point, I'm going to do the 3-second point first here. If I imagine the slope, if I would have a line going through just that point, that little line would be called the tangent to the curve, and it's a line that goes through just the one point. And the slope of that line can tell me the slope at just that point on the graph. It's gonna take me 1 or 2 tries for this. This one's way off down here, but we can imagine it'd be something like that. And that tangent line, the slope of that tangent line would tell me the velocity at that point in time, at that instant in time, because every instant in time, every single spot on this graph, on this quadratic function, has a different slope. The slope is getting steeper and steeper every instant of time. And maybe I have some sort of graphing software or something like that. And that graphing software is able to find me the slope at each of these points. And if I did that, I would find, for this data, the slope here is 4, the slope here is 8, the slope here is 12. And if you're taking calculus, or maybe taking calculus in the future, you would find out, they tell you how these are actually calculated by that software. But for now, we'll just go with what it tells us. 4 meters per second, 8 meters, 12 meters per second. So you can see my velocity is becoming more positive as time goes on. So now if I would make a velocity graph from this, again, even though I don't have any negative velocities here, I'm going to include the negative portion on the graph just to remind myself to check if I have any negative velocities. I don't, because I have no negative slopes of my position graph. And meters per second and time in seconds. And we're going for 3 seconds, and looks like my biggest velocity to worry about here is 12. So let's go 2, 4, 6, 8, 10, 12. I started at rest, so I started not moving. And after 1 second, I was going 4 meters per second. 2 seconds, I was going 8 meters per second. 3 seconds, I was going 12 meters per second. Again, drawing by hand, so this is not going to line up exactly, but we can see that that is a linear relationship. Each second, my velocity increased by the same amount, 4, 8, 12. So this is kind of cool. It's no longer a straight line like we saw previously at the buggy going at a constant rate. Now our velocity is increasing with time. So it is changing with time. There's a rate of change here. We can measure how much the velocity is changing every second. And this one we can do pretty easily because we can see it's a line. We know how to find the rate of change, the slope of a line like this. And there's going to be a very special word that we're going to use all year that relates with that. All right, and that word we're going to use is acceleration. Just like velocity is the rate of change of position over time, so it's the slope of the position versus time graph. Acceleration is a calculation of the rate of change, or the slope, of an object's velocity over time. So we're looking at the slope of the velocity versus time graph. So let's find the acceleration of this object. It doesn't say it here, but acceleration is also, whoa, finding my pictures, is also a vector quantity. It also has a direction. And in this case, the direction is going to be positive because we have a positive slope. So let's find the acceleration here. I'm going to look at the rise over the run. So I can pick anywhere because it's the same slope everywhere. Let's just do from here to here. It's moving over 1 second, and it's going up from 8 to 12, so that's a rise of positive 4 meters per second. So my acceleration would be the rise over the run, which would give me, it goes up 4 meters per second every second. So I get 4 divided by 1, pretty straightforward, 4 meters per second per second. Kind of a weird unit, right? Meters per second per second. So every second, this car, as it goes down this incline, its velocity is increasing by 4 meters per second in the positive direction. And we could have found that, we could have done 12. It goes up 12 in 3 seconds. We'd get the same thing. So this is a line. So every second, the velocity is getting more positive by 4 meters per second. In this case, it is speeding up. Right? It started at 0, so by getting more positive every second, it speeds up. Great. So that is acceleration. Now, is there any other tricks we can do with this velocity graph? There are. We can think, and we'll come back to acceleration in a little bit, but the other thing we can do with this graph, and I'm just going to move this up out of the way here, same with this, is we can think about displacement, because we saw in our previous model, our constant velocity model, that we could find the displacement of an object, its change in position, by looking at the area under the velocity versus time graph. And that was pretty straightforward because it was just a rectangle. We did the velocity times time. Here, it's going to be a little bit more complicated. but we can still do the same idea. So let's say I wanted to find the delta x, the change in position or the displacement from, let's say, from the first to the third second. How much did my position change going from the first to the third second? And you might say, oh, well, we can just look at our position versus time graph and that would work, right? You could say, well, at the first second, it was at 2. And the third second, it's at 18. So its displacement would be 18 minus 2, or 16 meters. We could also see that here, going from here to here, from 1 second to 3 seconds. It goes from 2 to 18. That's a change, a delta x of 16 meters. So we already know the answer to this. But let's say we didn't have that. Let's say we just had this velocity graph. There'll be many situations like this coming up. And I wanted to know that. Well, we know we can look at the area under the graph. Now this is not a rectangle like it was before. I can't just do 4 meters per second times the base here would be 1 to 2, 3 seconds, right? That's a change of 2 seconds. I can't just do 4 times 2 because this object is not going at 4 meters per second for those 2 seconds. At the very start it is, but then it's going faster. So 4 times 2, 8. 8 would be a real low ball estimate of how far this thing went. We can see it's less than 16. Okay, well, what if I use this 12? I do 12 times 2. Well, that's 24. I've overshot my displacement because it's not going at 12 meters per second this whole time. It's only going 12 meters per second at the very end. It was going less than that beforehand. So I can't just multiply velocity by time now to figure out displacement, but I can still think in terms of area under the curve. I don't, however, have a rectangle. I have this sort of parallelogram shape, and I guess you could look up the formula for the area of a parallelogram. That would work, but I find it's easier just to think in terms of, oh, I'll just split this up. Here I have a rectangle, and here I have a triangle, and I can just add those two together, and that'll give me the full area. Remember, for a triangle, we're doing a 1/2 base times height, whereas a rectangle, it's just base times height. So that's something we have to make sure we remember when we're doing the triangle part, that we include that 1/2. All right, so let's do each of these. I've got here, they both have a base of 2 seconds. The height would be 4 here. So I've got a height of 4 meters per second. Whereas the height here, what was that, 4 and went up to 12. So that would be 8 meters per second. Now we can just do base times height. 4 times 2 is 8 meters. And then 8 times 2 is 16, then 1/2 base times height. 8. And this is just a coincidence that these both ended up being 8. So my displacement here is going to be those two added together, 8 meters plus 8 meters. And it agrees with what we saw just by looking at our position graph. This object has changed its location over those 2 seconds by 16 meters, and this is going to be a positive. It's always good to include the positive to make sure we're reminding ourselves to think about direction. One of the easiest ways to make mistakes is not to think about direction in physics. It is 16 meters more in the positive direction from wherever it was at 1 second. If we want to do the full time interval, we know that should be 18 because we started at 0, we ended up at 18 after 3 seconds. We would just need to find this little spot here. So that would be a base of 1, a height of 4. It's a triangle, so I do 1/2, 1 times 4 is 2. And I'd add that all together. 2 plus 8 plus 8, 18. So over the full 3 seconds, this thing starting from rest, accelerating at 4 meters per second, ends up going 18 meters. All right, so that's the main ideas going on here. So let's do a little bit of a challenge. I'll give you another situation, deal with maybe some negatives and things like that. And then you can try it on your own, or you can walk through it as we go. So let's say, let me get rid of these so they're not in the way. Let us say that I have a blue car. And again, this is going to be motorless, so it's not going to power itself. It's just going to slide frictionlessly up or down this ramp. And let's say that that car has an initial speed of 12. Let's not do 12. Let's do something like 8 meters per second. And notice I said speed. Speed is just how fast. So when you're thinking velocity, you got to pause and say, what direction is it going in? And in this case, it's going up the ramp. And I said, well, I said down the ramp was positive. Up the ramp is negative. So this would be a velocity. Its velocity at 0 seconds is negative 8 meters per second. So that is very, very, very critical here. This negative is telling me it's going the other way. It's going up the ramp. And its starting position, we'll say, we'll measure from the front. At 0 seconds, it's right at that 16 meters. Now I want to know what's going on with this cart after 3 seconds. So we did this red one for 3 seconds. What's happening to this blue one during those 3 seconds based on the information I have here? It's at 16 meters at 0 seconds, and it's moving at 8 meters per second in the negative direction, in that case being up the ramp. One thing to note is that we found this acceleration of positive 4 meters per second, so positive meaning down the ramp. That's going to apply to any object on the ramp. So you can find out it doesn't matter what mass or anything an object has. If it's on the same ramp at the same incline, we'll experience this acceleration. So you can assume the blue buggy or the blue cart also experiences this acceleration of positive 4 meters per second. So maybe take a second. I will let you know you're going to need to start with the velocity graph on this one. So try making a velocity graph first of this blue car over the time interval of 3 seconds. And then check back here. We're going to do it right now. All right, so let's make a velocity graph. And here I'm definitely going to need the negative quadrant here for this graph. That's crooked. As our buggy here, our car, sorry, is initially moving in the negative direction. So let's go 2, 4, 6, 8. This is time. This is velocity, meters per second, time in seconds. -2, -4, negative. Oh, I can't do math. -6, -8. So initially, we know it's going at 8 meters per second. What else do we know? We know its position, and we know it has a positive acceleration of 4 meters per second. Just looking at our definition of acceleration, acceleration is the rate of change of velocity over time. It's the slope of the velocity versus time graph. So we know that this graph needs to have a slope of positive 4 meters per second. So what that means is after 1 second, if I was at 8, well, if I have a run of 1 second, my rise needs to be 4 meters per second, because that way 4 over 1 is 4 meters per second. Another way I could think about it, if I'm at -8, how many seconds to get to 0. It would be 2 seconds because I'm getting +4 every second. All right, so another second goes by, it increases by 4 again because that's the rate of change. So these aren't going to line up exactly, but let's redraw this one to fit. All right, so I used the acceleration to predict what the velocity is going to be after each second here. Oh, we can keep going. So it's still, it's still on the ramp. This car is going to go up. Here's where it stops, right? 0. After 2 seconds, it comes to a stop, but then it's going to start going back down the ramp, right? It's going to start going in the positive direction down the ramp. Going down, getting faster and faster. So here we'll see 3 seconds, it's going back the other way. Great, so that's my velocity versus time graph. Now I want to know where it is. I want to know where it is at each of these points in time. Where is it at 2 seconds? Where is it at 3 seconds? Where is it at 1.45 seconds or whatever? Let's mark. This should be 4 meters per second because, again, the slope is 4, so 1 second over, 4 meters per second up. All right, so how could I find those positions? Well, I could think about the displacement. I can figure out its displacement over the first second, and then using its initial position, I can figure out where it is next. So take a second if you want to try to do that on your own. See if you can figure out where is this object after 1 second, after 2 seconds, after 3 seconds. And we'll do it here together. All right, well, I know displacement is the area. So I'm looking for the area from the 0 second to the first second. And I can see 2 shapes here. I can see a rectangle and this triangle. All right, so the rectangle is pretty straightforward. 1 second, -4. Yes, we are going to use the negative here. -8 meters. And then here we have 1 second, -4 again, but it's a triangle, so we do 1/2. So you can think, okay, here's a rectangle, and the triangle is half of that. So 1 times 4 times 1/2. Oh, I can't do math. This should have been 4. Wow. Whoops. 4 times 1 times 1/2 is -2 meters. So we can see in the first second, I have a displacement of -6. Does that mean I'm at -6 all the way up here somewhere? No. This is displacement. This was change in position. So remember, the area is the change in position. So if I was at 16 meters, changed by -6, I've moved 6 in the negative direction. After 1 second, I should be at 10 meters. So here I am at 1 second. All right, and we can keep going. So if you were following along now, maybe try to go ahead now, figure out the second, and the third second on your own. Here we have 1 second, -4. Again, we have a triangle that ends up being -2. And we can see just graphically that these are the same size triangles. Well, maybe I didn't draw it well enough, but these should be the same size triangles. So from the first to the second, I had a displacement of -2. So I moved 2 more meters in the negative direction. So if I was at 10, 2 more meters. This was 10 meters. 2 more meters, negative direction. At 2 seconds, I'm at 8. And we can see this pattern again. Okay, I was moving pretty fast. I want a big displacement, a big change in position in the first second. Now I've gone a smaller change in displacement because my velocity, its magnitude, its size has gone down, right? I went from -8 down to -4. I say, well, haven't you gotten bigger because you're getting more positive? But remember, this negative just means the direction. So 8 is a bigger speed than 4. So I am slowing down here. All right, and then this last bit here, again, it turns out 1 second, 4 meters per second. This is going to be a positive 2 meters. So this object, it goes up, slowing down, slowing down, slowing down, slowing down. At that exact instant in time, at 2 seconds, it stopped. It doesn't stop and stay there, but for a moment, it has no velocity. Then its velocity starts getting positive, or positives down the ramp. Slower, 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 stop. And it speeds up, going back down the other way, right? We're going from 0 to a bigger number, 0 to 4. And so at 3 seconds, we're actually back where we were at 1 second. So we'll just put the dot right above it and say that's 3 seconds. Move this down so it's more obvious which one's which. So this is something we can do with a motion diagram. Two different points in time are at the same position. We just put one dot above the other one, like that. So it's gone at 1 second here, 2 seconds here, 3 seconds, it's back here. But going the other way, we could add our velocities to this motion diagram if we wanted to. So we already have the 8 meters per second. At 1 second, it's going 4 this way. And if I wanted to be technical here, I would draw this 4 meters per second arrow. So it was half the size of this 8 meter per second arrow. I think I made that one too big now. At 2 seconds, I wouldn't draw an arrow because at that very instant, it stopped. And then 3 seconds, looking at my graph, it's going 4 meters per second the other way. And we could use some little geometry things to show that those are equal in magnitude. These are the same speeds, but they are different velocities. This is a -4 meters per second if I'm talking velocity. This is a positive 4 meters per second talking velocity. Now I didn't put a negative here and a positive here because I have these arrows, and these arrows are already showing me the direction. If I didn't have these arrows, I would want to write the positives or the negatives. All right, cool. And if we continued this, you'd find out that at 4 seconds, it's actually back at the 16 meters because this area, and if I did this to 4 in this area, they would cancel each other out, right? I'd have the same negative triangle and the same positive triangle there. All right, cool beans. That is model 2, the constant acceleration model. We call it the constant acceleration model because this slope is constant. It's the same acceleration, 4 meters per second the whole time. You could draw, just for fun, you could draw an acceleration versus time graph, meters per second, and seconds. And it would just be a straight line at 4 meters per second because this slope is constant. And you'll notice they have, as we said, the same acceleration, same slope, even if they have different velocities and different positions and all that. They're going on that same ramp. Cool. Peace.